Okay, one more thing. We need to add some applications of isotopes. Number one, an isotope of uranium. Uranium is a radioactive element, is used as a fuel in nuclear reactors. Number two, an isotope of cobalt is used for treating cancer. And last, an isotope of iodine is used in the treatment of goiter. Okay. In today's lecture, we will be learning about the history of how this atomic structure was developed. We'll initially begin with Dalton's atomic theory. So, he proposed some postulates and those are, first is, matter consists of small indivisible particles called atoms. Second, atoms are neither created nor destroyed. Third, atoms of given element are identical in mass and chemical properties. Fourth, atoms of different elements have different masses and different chemical properties. Number 5, atoms combine with one another in simple whole number ratio forming simple whole number ratios forming compounds. Number 6. An atom is the smallest unit of matter which takes part in a chemical reaction and all chemical changes result from the separation or combination of atoms. For this point, if you write till here, then also it's fine. But if you want to be more precise, you complete this whole point. And last point, number 7, the relative number and kinds of atoms are constant in a given compound. Okay. Dalton's atomic theory was one of the earliest theory that had been proposed, and there was found to be many faulty statements in this, 3 of which are and this is our modern atomic theory. First point, atoms are indivisible and indestructible. But we know that modern atomic theory says that atoms are divisible as it contains subatomic particles like electrons, protons and neutrons, and destructible. Second point where it contradicts with the modern atomic theory is that an atom is the smallest unit of matter that is indivisible. But atoms are divisible consisting of subatomic particles like protons, neutrons and electrons. As a matter of fact, it has also been found out that the subatomic particles like protons, neutrons and electrons are further divisible. They are divisible into different types of quarks. Third point, atoms of the same element are alike in all respects. But in the case of isotopes, atoms of same element have, I'll complete this over here because it's just one line, different masses, or you can write atomic mass as well. This is the distinction or the faulty that was present in Dalton's atomic theory. We'll also see some similarities that were present between Dalton's atomic theory and the modern atomic theory. First of all, that an atom is the smallest unit of matter which takes part in a chemical reaction. This portion is true for Dalton's atomic theory as well as for the modern atomic theory, because it is the smallest unit of matter taking part in the chemical reaction. And second one is that the relative number and the kind of atoms are constant in a given compound. This is said by Dalton's atomic theory as well as the modern atomic theory. These two properties are the similarities between Dalton's atomic theory and modern atomic theory. Okay, now we'll come properly to the history portion of the chapter. First point is Sir J.J. Thomson studied the characteristics and constituents of electrons. It was then called as cathode rays. Since it's emerged from cathode. And he also proposed an atomic model He said that we can think of a watermelon positive charge in the atom is spread all over like the red edible part of the watermelon, while the electrons are studied, or you may just call it embedded as well, in the positively charged sphere like the seeds in the watermelon. You may also imagine this model as a Christmas pudding where electrons are like the dry fruits that we sprinkle over the cake, and the cake in itself is the whole positive charge sphere. Okay, so what was his proposal, or we may say what were his postulates? Number one, an atom consists of a positively charged sphere and the electrons are embedded in it. Second point, the negative and positive charges are equal in magnitude. So, the atom as a whole is electrically neutral. Think of it like this: if there is a certain positive charge and the same amount, same magnitude of negative charge is there, they will cancel out each other, and as a whole it becomes neutral. An atom as a whole is electrically neutral. Limitation: Thomson's model could not explain the experiments, or rather the results of the carried out by other scientists. Okay, so mass of an electron is 9.1 into 10 to the power minus 28 grams, which we consider negligible as compared to the mass of a proton. We'll also see the mass of a proton. We'll understand the difference between them in some time. Charge of an electron is 1.6 minus 1.6 into 10 to the power minus 19 coulomb. Coulomb is the charges unit. Next we have discovery of protons. Goldstein discovered protons from the positive rays emitted from anode consisting of canal rays. Canal rays are nothing but protons. Mass of a proton. Mass of a proton 1.6 into 1.67 into 10 to the power minus 24 gram, and charge of a proton is plus 1.6 into 10 to the power minus 19 coulomb. As you can see, the charge of an electron and the charge of a proton are same in magnitude but opposite in signs. And when we compare the mass of an electron and mass of a proton, we see that they differ by 10 to the power 3, that is 1000. Is the same like when you take the difference between 1 kg of any substance and 1 gram of it. So there 1 gram becomes almost negligible. Same is the difference between mass of an electron and the mass of a proton. That is why we consider mass of an electron as negligible. Next we will see Rutherford's atomic model. So, Lord Ernest Rutherford studied the atomic model and discovered the atomic nucleus. What he did was he directed alpha particles towards a thin gold foil There were reasons for this. First, he selected gold foil because he wanted as thin a layer as possible. This gold foil was about 1000 atoms thick. Okay, gold is the most malleable metal that is present in our planet. So that is why gold was chosen, because it can be beaten into as thin a sheet as we want. And 1000 atoms thick is a very, very thin metal sheet which he could use, and he could direct alpha particles to it. Also, we'll come about what alpha particles are. Alpha particles are positively charged helium ions since they have mass of 4U. U here denotes unified mass. We learned in the previous class that atomic mass unit in the modern time is denoted by U, which means unified mass. The fast moving alpha particles have a considerable amount of energy. Alpha particles are basically He2 plus ions. Okay. After completing this experiment, when he hit this alpha particles, fast moving alpha particles towards the gold sheet, some of his observations that we see are: most of the alpha particles went straight through the foil. What do we conclude by this? We conclude that an atom, and on the whole, is relatively empty. Number two, some alpha particles were deflected slightly. Conclusion: a concentrated positive mass is present in a very small region in an atom. And if the alpha particles is not close to the positive mass, it gets slightly reflected. Number 3, please note that these are points that you can make on your own and also write. Please do not mark them word by word. Some alpha particles were deflected by a large angle or bounced back with a 360-degree deflection. If the alpha particles passes very close to the nucleus, it gets deflected through large angles. And if it approaches at right angles, it gets deflected by 360 degree. The results are something you can also make on your own and write, but remember the observations. All 3 observations are important here. So what postulates did he conclude after this? First, there is a positive charge center in an atom called the nucleus. Nearly all the mass of an atom resides in the nucleus. Number 2, since the atom is neutral, electrons must revolve around the nucleus to counterbalance the positive charge, for the atom to be stable. And number 3, the size of the nucleus is very small as compared to the size of the atom. Okay, let's look once at how how the helium particles hit these atoms and how they get deflected. So most of them went undeviated. The ones which were quite close to them got deflected by a small angle. Not very close, but a bit close, got deflected by larger angles. The ones which were very close got deflected by larger angles, and the ones that hit at right angle, this forms 90 degree over here, got deflected completely by 360 degree. This is what he concluded after this experiment. This is the nucleus and this whole is an atom of gold. Okay, so what were his drawbacks? The revolution of the electron in a circular orbit is not expected to be stable. Why so? Any particle in a circular orbit would undergo acceleration. We'll learn about this acceleration in physics in more detail, but what happens is whenever any particle changes its path, its velocity changes. As there is change in velocity, there is acceleration. As there is acceleration, there is some force needed. Force is a product of mass and acceleration. Now, if force is there, work done is there. Work done needs energy. During acceleration, charged particles would radiate energy. And thus, the revolving electron would lose energy And finally, following a spiral path would fall into the nucleus. Hence, Rutherford's model could not explain the stability of an atom correctly. Okay, with this we conclude Rutherford's atomic model, and the last model that we follow and we are going to learn is the Niels Bohr's atomic model. Okay. His postulates: number one, only certain spatial orbits known as discrete orbits of electrons are allowed inside the atom. Number two, the integer n represents the various discrete orbits also called energy levels one, two, three, and so on, starting from the innermost. The labels are also designated as K, L, M, N, and so on. And the third postulate of Bohr's atomic model is that while revolving in discrete orbits, the electrons do not radiate energy. Okay, these are the three postulates of Bohr's atomic model, and last we have the discovery of neutrons. James Chadwick in 1932 discovered the subatomic particle which had no charge and atomic mass nearly equal to that of proton. It was eventually named as neutron. Neutrons are present in the nucleus of an atom. Mass of a neutron one 1.676 into 10 to the power minus 24 gram. This is quite similar to the mass of proton. Mass of proton is 1.67 into 10 to the power minus 24 gram, and this is approximately 1.676 into 10 to the power minus 24 gram. Charge of a neutron, it does not have any charge, it is neutral. With this, we come to the end of this class and also this chapter. In the next class, we'll start with a new chapter.